This is activity 2, one scenario, 4 representations, from lesson 14, 4 representations. And in this activity, students are to choose 2 different properties and put together scenarios for a proportional relationship between those properties. So you select 2 things. I like to call these properties. I just like that word better. So 2 properties from this list make up a situation where there is a proportional relationship between the quantities. It means numbers that involve these things or these properties. Now, as I looked at this list, there were several that I wasn't sure what they were. So one of the things that students might do is look up some of these things. I didn't know what a cubit is, although I think it has to do with ancient Egypt. A parsec has to do with measurement in the universe using astronomy or outside the Earth. Square microns. I think a micron is 1/1,000,000th of a meter, but you might have to look that up. Hides, that's a measure that trappers used to use that would trap animals and collect animals' fur. They would trade in hides. A deben is an ancient Egyptian measurement, and I actually did look this one up because I think it might have to do with debt, D-E-B-T, compared to deben. And a deben has actually 2 different measurements. In ancient Egypt, one measurement is 13 6/10 grams, depending on the kingdom. And another kingdom, the New Kingdom, I believe, it was 91 grams. So you have to think about that a little bit. What is a pitch? Now, I know what a pitch is in soccer, but what's a pitch as far as a substance? And so you choose 2 of these things. Now, you might have to choose 3. You might have to choose a creature, for example, and then look at the speed that creature moves. So that would be length per time, or how much of a certain substance it takes to fill a container. So gallons per minute to fill a container with the substance of helium, something like that. So you might have to use a creature, a substance, and then a couple of different properties of either a creature or a substance. It is clearly up to you what students do. And then metric tons. I know what a ton is in the United States. It's 2,000 pounds. But what's a metric ton? And why is it spelled with an N-E-S? Is that just an English spelling? So this would be a metric measurement. So, what's a metric ton? Millennia I find interesting because milli shows up as a milliliter, which is 1,000th of a liter. But then in a million, it's 1,000,000 things. So that's more than 1,000. So why isn't millennia equal to 1,000? It's equal to 1,000. Why not 1,000,000? So what's the relationship between million and millennia and 1,000? And the answer is that a million is 1,000 thousands. So there is a relationship to 1,000 in the word million. So different things going on here. And finally, nanograms. Nanogram is 1/billionth of a gram. A microgram is 1/1,000,000th of a gram. So different things to think about. Here's the form for students to fill out. I provided this in as a PDF in the information below this video. And so you go through each of these, you fill in what the properties are that you're looking at. And these are the 4 representations: a verbal description, a table, a graph, an equation. Those are the 4 representations. Then they ask the student to explain in words what the letters mean in their equation and what the numbers mean in their equation. And how do you know that it's a proportional relationship or not a proportional relationship? They do ask students to put together situations that are not proportional, but I would just focus on proportional relationships. Now, this is the time for students to start solidifying their understanding what a proportional relationship is. They should write out in their own words what they think a proportional relationship is and begin to refine that over time, make it better and better and more understandable to the student. So each student might write something different. So what is a proportional relationship? For me, it has to do with a comparison of two properties through multiplication. So you're using multiplication to compare two things. And you get into the issue of thinking about a scale factor or a constant of proportionality. If both properties move together, that's usually using the scale factor. But if you're using one factor to multiply one property to get to the second property, that's the constant of proportionality. So it takes some thinking to sort through that. What kinds of situations can be represented by a proportional relationship? Speed, miles per hour, feet per second. Cost is a common one, dollars per pound. So you might post on the wall somewhere in your classroom, how many different ways can you put together situations that are represented by proportional relationships? What form does the equation of a proportional relationship have? So this is the y equals kx. So it's two factors. This is a basic multiplication fact, but one of the factors is the constant of proportionality. The second factor is usually the independent variable. That's the x coordinate or the x value. So what are you given? And then you want to figure out what the dependent variable is based on what you're given. So what's the result of the calculation? That would be the y value or the dependent variable. And what does it mean, y divided by x? That's the constant of proportionality. And there's a graph, a common graph that goes along with a proportional relationship. Straight line, it goes through 0. This is where you think about a constant of proportionality that's less than 1 or a constant of proportionality that's greater than 1. So for every proportional relationship, there's two graphs, there's two equations. And think about the reciprocal nature of that constant of proportionality. So in one case, you can think of it as the constant of proportionality. In the second equation, or the second graph, you can think of the constant of proportionality as the reciprocal of the first constant. They are multiplicative inverses. That is called a reciprocal relationship. So lots to think about. So students should start to put together their own thoughts on what a proportional relationship is. There's a table. There's a change in one quantity. What happens to the other quantity when you change one quantity, 1 unit? That's the unit change or the unit rate. What happens to the dependent variable when you change the independent variable by 1 unit? Now, one thing that you might do is go through the lessons in this unit and list each of the proportional relationships. And don't go through solving it, thinking about it too much. Just get an idea of the different situations that we use throughout this unit for proportional relationships. This is from lesson 1, which was 3/2 teaspoons of a powdered drink per 1 cup of water. So that was one proportional relationship. The second one was 1/2 of a teaspoon of powdered drink per 2 cups of water. And a third proportional relationship is 1/4 teaspoons of powdered drink per 1 cup of water. And 2 of these are the same and 1 is not. And the 2 that are the same are these 2 right here. Because if you decide to use half the amount of water, that's 1 cup of water, you're going to use half the amount of powdered drink. So 1/2 of 1/2 is 1/4. So different proportional relationships. So just a simple list of these might be helpful for students to look at and think about. When I started thinking about this problem, I thought of Mount Everest. When I used to teach earth science, I learned that Mount Everest, the height of Mount Everest, is actually changing. And so I looked it up, and it turns out that they recently measured the height of Mount Everest and found it had changed by about 3/4 of a meter. So this is the current height of Mount Everest as measured in, I think it was 2020. So I provided a link for this, a QR code, so students could do a little bit of reading about how they did that and just what was the change over time. And it turns out that it's changing about 4 centimeters per year. And so then I began to wonder a little bit further on this as how much would that change be in a century? So basically a very long lifetime. How much does Mount Everest change over 100 years? And here's the QR code that will take you to that link. I also provided it as a PDF, so you can either click on the link or just scan the QR code. And so 4 centimeters per year means that in 100 years it changes 400 centimeters. So how much is that in inches and in feet? Something I understand a little bit more is if I can figure out the number of feet per 100 years. Well, 400 centimeters divided by 2 54/100 centimeters is going to give you the number of inches. Well, where does that come from? So the relationship, and remember this equation right here, this is the equation for a proportional relationship. And so a conversion is a proportional relationship where you change from one unit to another unit. So if I write this as y inches, I want to calculate the number of inches. I want to get to this 157.5 inches. So I'm going to multiply the number of centimeters by some value. So it's 400 centimeters. And so then the question is, do I multiply it by 2 54/100 centimeters, or do I actually divide by 2 54/100 centimeters? Well, inches is a larger unit than centimeters. So to measure the same length in inches, you're going to use fewer inches than you're going to use centimeters, because centimeters are smaller. So you're going to end up making this amount smaller. So you're going to divide by 2 54/100 centimeters. That's the same as multiplying by the reciprocal. So this is 1 over 2 54/100 centimeters times 400 centimeters. So notice that it's division right here. 400 divided by that 2 54/100 centimeters. So you're going to change this. I changed it to division and using the reciprocal of this relationship. So you're dividing, so it's 1 over 2 54/100 centimeters. So every time, the way to look at it over here is every time you take out 2 54/100 centimeters, that's an inch. So how many times can you do that? You can do that 157.5 times. It's the same as multiplying 400 centimeters by 1 over 2 54/100 centimeters. And then you want to change the inches to feet. Well, the relationship between inches and feet is that there are 12 inches in 1 foot. So now you're given the number of inches and you want to calculate the number of feet. So am I going to divide or multiply by that 12? Well, feet is a larger unit of measure than inches. So you're going to use fewer feet. So you're going to have to divide this number. And each time you take out 12 inches or you divide by 12, that's 1 foot. So how many times can you do that? You can do that 13 1/10 times. So there's 13 1/10 feet per 100 years that Mount Everest grows. So over here, you're going to multiply by 1 over 12. And notice that ends up being 157.5 inches divided by 12 inches. So this is in effect dividing. You're making this value smaller. All right, fill in a table. So the first thing I did is, so here are the quantities up here, centimeters and years. I want to look at the proportional relationship of Mount Everest increasing in height over years. So Mount Everest increases in height very slowly at a rate of 4 centimeters per year. A graph that shows centimeters are proportional to years. So you want centimeters that are proportional to years. So if I write it that way, that means that it's centimeters per year. And that means that the y-axis is going to be labeled centimeters. And the x-axis is going to be labeled years. Centimeters per year, y per x. So how many feet in a century? So over here, the x value is years. So it's y per x. It's going to be centimeters per years. So x is going to be years. That's the given amount. That's the independent variable. So in 5 years, how much did Mount Everest grow? So that's going to be the dependent amount. That's going to be the calculated amount, or the y coordinate. So increase in height. So we know that it increases in height 4 centimeters in 1 year. So 4 divided by 1 is equal to 4. So the units in height are 4 times the units in years. So every time I have a unit in years, 1, 2, 3, 5, 10, or even x, I multiply that by 4 because the units in height are 4 times larger. So 2 times 4 is 8 centimeters, 12 centimeters, 20 centimeters, 40 centimeters, and finally you get down here to the equation, which is 4x, 4 times whatever the value of x is equal to y. So y is equal to 4x. So y equals 4x, and that's centimeters. The height of Mount Everest is equal to 4 times the number of years. Now these are different y's. This y right here is the y coordinate. This y right here is years. So be careful about that. But the equation is centimeters equals 4 times the number of years. C equals 4y. Put together a graph. First of all, you have to think about what to label the graph and what to label the units on the grid. And so along the bottom, years, it's pretty easy. You just label 1 year per unit, 1 year per line. But along the y-axis, each line, you have to think about that a little bit, because if you labeled 1 centimeter per line, you're not going to get out very far. And if it changes 4 centimeters a year, it probably makes sense to label each of these lines 4 by 4 centimeters. So it's 4, 8, 12, 16, and so on, up to 60. 4 times 15 is 60. So you get up here to 60 centimeters. And Mount Everest height, it increases. So this is a title. And you want to make sure that you label it years is equal to 1 year is equal to the year 2021. So this year, and in 1 year, it increases in height in centimeters. Okay, the increase in height of Mount Everest, y is 4 times the number of years, because the height increases 4 centimeters per year. So these are the different values on the table. So I graph them. They fall in a straight line. It goes through 0. So 1 year, 2 years, 3 years, 5 years, and 10 years. 10 times 4 centimeters per year is 40 centimeters. So y is equal to 4 times 100 years. So that goes way beyond the graph. So this is an example of where you figure out what the equation is, and you use that for values that are far beyond what's shown in the graph. So y is equal to 400 centimeters, 4 times 100 years, and we figured out from before that 400 centimeters divided by 400 centimeters is 157.5 inches, and the number of feet, now you can start to see that this number has to get smaller by dividing by 12. So the number of feet is 157.5 inches times 1/12, or divided by 12, equals 13 1/10 feet per 100 years. And so using the graph, you read up from 3 years, you can read up and see that that's 12 centimeters in 3 years, where these two lines intersect, the line along the x-axis and the line along the y-axis, they intersect on the graph. That's the answer to the equation. 3 times 4 is equal to 12. So this line, this graph, is 4 times the value of x. So 4 times 6 is 24. So if it's 6 years, 4 times 6 is 24 centimeters. So you read over here to the y value. On the y-axis, that tells you it's 24 years. Here's an example that the authors provide. And so I'm going to zoom in on this. I gave this to you also in the description below this video. I provided a link for this image. I'm not going to go through this in too much detail. They talk about a three-legged race, so you're going to travel yards in minutes. So they travel 100 yards, so Adon and Mike travel 100 yards. And they have a marker, 1/2 minute, 40-yard marker at 1 minute, and 60-yard marker at 1.5 minutes. So as they're traveling, they travel, what's the distance they travel in an amount of time? So it's actually time per distance. So 20 yards, they travel, it takes them 1/2 minute, 40 yards, 1 minute, 60 yards, 1.5 minutes. So you might read through that again. Here's the graph. The problem I have with this graph is they didn't tell you the units of time. So you have to tell people that this is minutes. Otherwise, they don't know what time this is. It could be years, could be months, but it's minutes. And this distance is yards. So again, you have to label what the unit is for the distance. This constant of proportionality is 1/40th, but what does that mean? Well, the constant of proportionality is time per distance. So the time per distance is 1/40th of a minute per 1 yard. So that's where you get this 1/40th from. So it's 1/40th of a minute per 1 yard. So then if you travel 2 yards, it's 2 times 1/40th. 3 yards, 3 times 1/40th. Travel 40 yards, it's going to take you 1 minute. Travel 80 yards, it's going to take you 2 minutes. So this is 1/40th of a minute per yard. And that's written down here. 1/40th is the constant of proportionality. It takes them 1/40th of a minute to travel 1 yard. And explain what each of these values mean. So you might read through this carefully, think about it, have a class discussion of what's going on. And remember, it follows this equation, y equals kx, or distance is equal to the constant of proportionality times time. So what's the distance in 1 minute, 2 minutes, 3 minutes? They reverse this. This should be time equals k times distance, because it was time, the amount of time is equal to 1/40th the distance. So if they ran 40 yards, that was 1 minute. 80 yards, that was 2 minutes. So they reverse this. Because if we go back to here, this is time equals kd, where k is the constant of proportionality. So time equals kd, time equals kd. So this should be reversed. So each value of distance in the table can be multiplied by 1/40th to get the corresponding value of time. So time equals the constant of proportionality times distance. Graph is part of a line that goes to the origin in quadrant 1. The equation can be written in the form, it can be written in this form, and that would be distance is equal to 40 times the amount of time. So in 1 minute, they travel 40 yards. In 2 minutes, they travel 80 yards. But that's not what this problem is saying or how this problem is set up.